One. All right, welcome everyone. Welcome. It's February 12th, 2018, Monday night. We are in Pierce 116. The studio audience is here to help me cheer me on to go through one of our exams. So I want to begin by thanking our volunteer cameraman who stepped up to the task. And without that, we wouldn't have this uploaded on YouTube. So Jonathan, way to go. Okay. All right. Now, what my goal is tonight is to make this time worth your while, whether you're in the home audience or in the studio audience. If you're here, you have got to ask questions if I'm saying something that doesn't make sense. Because chances are someone out there in the home audience is throwing popcorn at the screen because they have the same question and you're not asking it. All right? So my goal for tonight is to go through a previous exam. So I'm going through the most recent exam we had, Fall 2017, Exam 1. Now you'll notice there's multiple versions. I picked version 1. Now I would like to say an important point. Right before we started tonight, I posted quiz 2 with solutions. Now you might say, well, what are you doing posting quiz 2? Some semesters we didn't get as far as you have with me, and Thevenin was not on quiz 1. So if you go to a quiz 1 and there's no Thevenin problem, just go to that same year, same semester, quiz 2, and you'll see a Thevenin problem. Okay? So the exam covers chapters 1 and 2 through Thevenin. So Thevenin is on it. All right? So what I'd like to do is to go through an exam that we gave just last semester, Fall 2017, quiz 1. Now, I know I said this in class. I just want to say it again. The trap in this course, and it's not meant to be a trap, is if you open up the solutions the night before the exam and you go through the solutions, I bet you'll follow them and you'll understand them. The challenge is to not look at the solutions. Pick up the file that just has the questions. Now, how do you start? I was talking to a good colleague about this right before the filming tonight. And the best way to do this is to start going over exams. Start with the most recent semester, Fall 2017. And maybe set as a goal, as a minimum, 3 semesters of exams. Now, the first time through, if you get stuck, look at the solutions. But by the time the exam comes, how about this as a goal? You should be able to pick up the last 3 semesters' exams, one version, and go through it all in about 50 to 55 minutes. That would mean you're ready. Okay? So let's begin that process by going over one of them tonight. So I have in front of us here Quiz 1, Fall 2017. And I ask, okay, how many questions are there? In this exam, there are 4 questions. Hopefully the topics don't surprise you. Nodal, mesh, amplifier, and some challenging problem on circuit analysis. So let's go through it. Let's take them one at a time. Problem 1. All right. Now, I'll give you a moment to write it, but as you're writing it, I need to tell you this dotted line and the word supernode is not on the exam. That's part of the solutions. Okay? So when you look at the exam, don't look at the solutions first. Look at the copy with no solutions. And you'll have to recognize yourself that's a supernode. So it says here, consider the circuit below using nodal analysis. Write, do not solve, all the required equations to determine V1 and V2. Clearly label these equations. And again, I say, do not solve them. Okay, we don't have, I don't think you would have time to be able to solve all of this. Now, once again, that supernode is not designated on the question sheet. You have to know that. Fantastic. How do you know it's a supernode? Excellent. A supernode is a voltage source. Whether it's a circle or a diamond, as long as it's a voltage source. Now, how do I know it's a voltage source? It's like a battery, plus minus. It's a voltage source between two nodes, and neither node is ground. So it's a circuit, excuse me, it's a voltage source between two nodes, and neither node is ground. Did I do okay? Now, part of this problem is knowing how many equations to write. So I always ask myself the following three questions. So let's see if we can do this together and get into the habit of this. How many nodes are there in this circuit? I count V1, which is labeled, V2, which is labeled, and ground. So I count 3 nodes. How many nodal equations do I need? Exactly. N minus 1. I need 2. So right away I know I need 2 nodal equations. I have a question from Emily.
What if they did not label like V1 and V2? How would you know where the nodes are?
Right. That would be the way, yeah, the question is, what happens if I didn't label V1 and V2? My concern there is, yes, I'm hoping you would recognize this as a node and that as a node, but then you might call it V1, V2, someone else might call it VA, VB. It would be a disaster to grade. Now, I sense your question is, how do you know it's a node if this wasn't here? A node is a connection of 2 or more wires.
Why is that one not a node?
Why is which one not a node? Here? That is a node. It's all the same node. Emily, help me out. You're raising a key question. Emily, all of this line from here to here has the same voltage with respect to ground. See, I can slide my finger along here, and I'm touching nothing but the wire. There's no resistor or anything. So this is all electrically the same point. So I sense you were looking here. This point here electrically is the same as this point. It's the same node.
So what happens if you put a resistor in between?
If I put a resistor in between, this becomes V1, this becomes some other voltage. It's, all right. Emily, did I get it? And Emily, is the same over here? Yeah. This entire path from here to here, right, including the top of this resistor, right? Everything here is the same electrical voltage. It's only a perfect wire. That's all one node. And Emily, are you okay that between here is a supernode? I didn't write this on the exam, and I didn't put a little circle around it. All right. So how do I know it's a supernode? Perfect. Voltage source between 2 nodes, and neither node is ground. Okay? You got it. Okay, perfect. All right, so I now know there are 3 nodes, so hence I need 2 nodal equations. The next thing that happens, do I have a diamond? Yes. That means I need an additional equation. So now I'm back to 3 equations, or I'm up to 3 equations, not back. I'm up to 3 equations. Next, I say, is there a supernode? So I look for all the voltage sources. And is any voltage source connected between 2 nodes with neither node is ground? That's a supernode. So those are the 3 questions. How many nodes? N minus 1 nodal equations. Are there any diamonds? And then after that, or whatever order you wish, is there 1 or more supernodes? So now I got the scope. I circle the supernode. And now I'm going to start writing equations. So let me write them, and then we'll check and see if I'm right. Okay, with the answer key. So I'm going to walk over here to the side of the board and start writing the equations. Now, I'm in node 1. Okay? I'm in node 1 on the left side. Okay? But I noticed that what we have here is a supernode. So it's all one big node. I'm going to treat node 1 and node 2 as all one big node. So here's what I have. I have minus IS. Why minus IS? Because the current's going in. Now, whenever I can, I assume the current is going out. So this becomes then V1 minus 0 over R1. Exactly. So I can't write on the screen, so you'll have to forgive me. I'm assuming this current is flowing out, which is V1 minus 0 over R1. Now, as you point out, I have a controlling variable here, which I'm going to get to. So that's going in. So what you could have done is instead of this term, you could have written minus IX. Did I do okay? Whichever one you wrote, you'll see in the answer key, you were fine. Now, I then come over here, and I get V1 minus 0 over R2 plus R3.
I just have a question about the original one before. If you wrote minus V1 over R1, would that be correct?
If I wrote minus V1 over R1, would that be correct? That would not be. That would be assuming that the current is going in, I think, right? Yeah. We're taking the case that unless I'm told differently, the current flows out. So in terms of this, it's V1 minus 0 over R1.
Okay.
I sense I didn't connect. Help me out.
Because you said you're not unless you're not told differently, but I think you are being told differently if there's an IX.
You are, but that doesn't make it minus V1 over R1, does it?
So it has to be a current.
It does. It does. So if you wanted to write here, what you're saying is IX equals minus V1 over R1. Do you see that, sir? If you do, then you're going to be helpful later on when we look at the controlling variables. What is this current that, imagine there was no IX, and you just looked at the current flowing down. The current flowing down is V1 over R1. IX is flowing up, so it's the opposite. So IX is minus V1 over R1. Did I get it that time? All right, good. All right. Now, I now go to that third branch, and what I get is plus V1 over R2 plus R3. V1 minus 0 over R2 plus R3. How am I doing? Ask questions. All right. I now jump to the other side of the supernode. And what I get is plus V2 over R4. Now notice the next current source is flowing out, which is good. By the way, forgive me, I miscounted before. My apologies for the archive colleagues who have been yelling at me. There's 2 diamonds. Right? So how many equations do I need? I have 3 nodes, so I need 2 nodal equations. How many diamonds do I have? Please forgive me, 2. So I have to write 4 equations. All right? So I then get V2 over R4, then plus B Vx plus V2 over R5 plus V2 over R6 plus R7. And Jonathan, I'm going to try and squeeze into a equals 0. Now, let me just slide down the PDF file. How did we do? How can I help?
So, if there's a supernode between V1 and V2, you'd write it like that. But if there wasn't a supernode, would it be like V1 minus 2, V2 over the resistor?
Right, I need to be careful because we're changing the problem now with your question, but your question is interesting. If this was a resistor here, okay, so my colleagues, I'm now temporarily changing the problem. If this was a resistor, there'd be no supernode, and then you would just have a term here that would say V1 minus V2 over R.
So if there is a supernode, you don't write it that way?
No, if it's a supernode, first of all, a supernode is a voltage source, right? Now, in your example, when this was a resistor, we said V1 minus V2 over R, right? That's the current. Here's the problem with a supernode. What's the current through that voltage source? No. The current through that voltage source is not IX. IX is the current way over here. IX controls this voltage source. See, I don't know what the current is. It's an unknown. See, it's not a resistor. Notice everything here works well if it's a current source or a resistor. If it's a voltage source between two nodes and neither node is ground, I don't know how to handle it easily, so it becomes a supernode. Did I do okay? All right, good. Everything else good? Tara, how can I help?
If the arrow, like for BVX, is facing up, then would it be negative?
Right. Tara is saying if the arrow was pointing up, it would then go in. And if it goes in, just like IS did, it would be minus. So in is negative, out is positive. We're good? All right. Now, notice we got the equation, but our colleague has already helped us that V1 over R1 is minus IX, which was your point earlier. There is another point here. V1 over R2 plus R3. Let's just talk about that. That is this one right here, the third branch from the left. You see this here? Getting back to the last question, I want to know the current through here. I want to know the current through this branch. So moving over to this side of the board, what I will say is that current is V1 over R2 plus R3. But there's another way to write it. It is V1 minus a minus Vx over R2. That's the same as this. You see, V1 minus this voltage. We started out at ground and we went down. So this voltage right there is minus Vx. So what's the current through this branch? V1 minus a minus Vx over R2, or V1 minus 0 over R2 plus R3. Isn't that cool? So I'm just going to slide down the work here. All right, so now we have one equation. Now, what has to happen next is we now have to walk through the supernode. So we're going to walk through the supernode. Now, let me see if I can do this, because I think it's important enough for me to do it. I'm going to raise the screen just a little bit. I hope for the home audience this is not too hard to see. Huh? Comes out good? Thank you, Jonathan. My colleagues, you now have to walk through the supernode. We don't have any equation with that voltage source in it, and I need it. So my colleagues, I know I've mentioned this in class at least twice. I want you to hear it again. Before you go through the supernode, you have to prepare for the walk. So you put down plus, minus. And all of this is V1. Plus, minus, V1. How do I know it's minus at the bottom? That's ground. I now come over here, and this is plus, minus, V2. Again, plus on top, minus on the bottom, because that's where the ground is. And what do I do next? I now have to walk through the supernode. Now, you can start anywhere. I start at the bottom left. Now, you could do plus Vx, but then you'd have to write an equation probably with an I and an R2 here. That's another unknown, Danielle. I don't want to have any more unknowns. So I'm going to keep things real simple. This here, from this point to this point, is minus V1. See, remember, what do I want to solve for? V1 and V2. So what I have now is walking through the supernode, I get minus V1. Now I then hit that diamond, I get plus AIX. I now come down, I get plus V2, and all of this equals 0. So how many equations do I have now? 2. How many do I need? 4. We're halfway done. Da-da-da. Now, the other 2 equations I need are for the diamonds. You already helped us, good man. I now go to this diamond. And my colleagues, I know I've kind of done this in class to help reinforce it, but I want to do it one more time. I come to the diamond and I say, what's the controlling variable? IX. Now, if I stay here and just look at IX, I'll get nowhere. I have got to find where is IX defined in the circuit. IX is defined here. Now, the easiest way that I know how to think of this is IX is the current through R1. Now, suppose I were to ask you, what is the current coming down? I bet you'd get it. V1 minus 0 over R1. This current is going up. So it must be minus V1 over R1, which is what we had earlier. So this is the third equation. The last equation, I go find the other diamond. It's Vx. Now, I'm not going to stay here looking at Vx. Jerry, I got to go find where Vx is defined in the circuit. So I come over here, and this is Vx. So I got to look here. Now, let me show you how I did it. Okay. What you can do is you can use voltage division. Okay. So what I'd like to do is to put down the screen now. And now I would ask myself, what is Vx? Now remember, what's the unknowns? V1 and V2. So I want Vx in terms of V1 or V2. Now, suppose this was plus and minus Vx. Just suppose. If this was plus and minus Vx, I'm asking you for the voltage across R3. And the voltage across R2 plus R3 is V1. So, Gina, V1 is going to divide sum over R2, sum over R3. So, if, I'm still saying if, this was positive negative, I would write V sub x equals R3 over R2 plus R3 times V1. Now, that's not exactly true because Vx, Parker, I see you. Help me out here. I see you got this. What do I have to do, Parker, and why? Why do I have to make it negative? You're absolutely right. Why am I making it negative? Right, because it's going, right, because it's, instead of being positive, negative, which we would expect since this is ground, it's upside down. It's negative, positive. So what we then get is we have to make it negative. My colleagues, those are the 4 equations, and that is problem 1, part A. How are we doing?
Can you go over the last one?
Sure. Question is, can I go over the last part again? Help me out. What do you see? Do you see the voltage division? Right. The question is, how do I know it's R3 over R2 plus R3? So the voltage from here to here is V1. Now, part of that voltage goes here, and part of that voltage goes here. For voltage division, we put in the numerator. Sorry for the background noise. In voltage division, we put in the numerator the resistor whose voltage we want. So I want the voltage across R3. So it's R3, and then over the sum of the 2 resistors in parallel in this case. It's not always 2 resistors, but in this case it's 2. So that's R2 plus R3. And then that sets up a fraction of V1. So I then multiply that by V1. And are you okay with the negative sign? Good. All right. Tara, help me out.
If there were resistors on top, like right after V1, before you get to the next line, then would you include that in the denominator of that equation or no?
No, that would be a different voltage, Tara. You're making harder questions than I did. I'll have to listen to this video to see what I can do. Your question is, if there was another resistor here, that would make this another node.
Okay.
This would be V3, for example.
Yeah, so you wouldn't include it.
You wouldn't include that because I would include this voltage from here to here.
Okay.
Tara, did I do okay? Yeah. Parker.
Then would that mean V1 is not part of the supernode and V3 would then be part of the supernode?
Yeah. My colleagues, I love these questions. I am a little hesitant to go down this path because we're changing the problems in real time, and people are throwing things at the screen. I can see it already. Parker, if I were to put a resistor here, this now becomes, V1 is no longer part of the supernode. But whatever this node is becomes part of the supernode. I prefer for now, let's see if we can solve the given problem. Okay? As you start throwing more curves, it just makes it difficult. Okay? But you are right. I can throw a curve. But let's master this level first. Sounds good? Thanks, Parker. Thanks for your understanding. Now, we're not done with problem 1. Problem 2. Determine an expression in terms of V2 for the power delivered to R7. So I say, wait a minute, where's R7? Ah, now this is voltage. I'm tempted to call on my good colleague here, but I won't. But this is voltage division. We want to know the power to R7 in terms of V2. Now, how do I relate power to voltage in a resistor? Over R. So power is V squared over R. What I need to know is the voltage across R7. Before I show you the answer, what's the voltage across R7? Who can help me out? Who can help me out? Voltage across R7. Danielle. V2 times R7 over R6 plus R7. I knew you were going to say that. So that's voltage division. Now let me write that again. Jonathan, did you have a comment? Okay, we're good? All right, my colleagues, I know I said that very quickly. Let's go through it. The voltage across R7 is exactly what Danielle said. It's R7. Why is it R7? Because I'm using voltage division, and that's the resistor whose voltage I want. It's R7 over R6 plus R7 times V2. Now, that's the voltage. Now, how do I get the power? You already told me, V squared over R. Just plug it in, and you get a result. Emily? I think that's an easy simplification to get like that. You're fine. This is easy. This is easy, right? This is just distributing the square. V squared. This is boom, boom, boom. Then I just cancel out the R7 squared and the R7. Could you just leave it like this? Probably, sure. Okay, but if they take off points, then you'll have to come and see me. But really, this is 30 seconds work. 34 seconds work. Okay? All right. I'll leave it up to you. There are two other ways to solve this problem also, using I squared R and P equals IV. So there's a total of 3 ways of doing it. I showed you what I think is the easiest, but you could have done one of the other 2 ways. I'll leave that up to you. God bless. All right, let me pause. That's our first problem. What do you think? Easy, medium, hard? Okay? Okay. Medium. All right. Okay. Part B is the second way to solve, and part B a third way to solve. I'll let you, work it through, my colleagues. Consider the circuit below using mesh analysis. Write, do not solve, all the equations to determine I1, I2, I3. Clearly label all required equations. Do not solve. Now, my colleagues, my handwritten notes, including the X, were not on the original exam. So the X and my handwritten notes were not there. So Parker, I look at this and say, all right, can I figure out how many equations? There's 3 diamonds. Middle, top right. Look. Yeah, I missed a diamond in the first problem, so forgive me. Yeah. So there's 6 equations. Because I have to write an equation for I1, I2, I3, and for each diamond. That gets me to 6. Now, is there something else shouting at us? Maybe all the way up to SUNY Albany. Is there a shout going out? And it's telling us something. What is it telling us? Jerry, there's a super mesh. A super mesh. A super mesh is when you have a current source shared by 2 loops. I hear all the lacrosse team is talking about this. This is all the buzz on the lacrosse team when they're out there yelling and practicing and hitting each other. They're saying super mesh, super mesh. All right? So it becomes a current source. I hope I didn't say voltage source. It becomes a current source. Again, I hope I did not say voltage source. I don't think I did, but just to make sure. It's a current source between 2 meshes. Now, the current source could be a circle or a diamond. It doesn't matter. Remember, how do I know it's a current source? The arrow. Excellent, Emily. So now we have the idea that this is a super mesh. Help me out, my colleague.
Is that a supernode in the top right? Or are we not really worrying about that?
This is a great, and Jerry, this is what you may have meant, and I apologize. The question is that a supernode on the very top? It is, because it's a voltage source between 2 nodes, and neither node is ground. However, we're not worried about it, because we're not doing nodal. you raised an excellent point. What we're doing is you and I are about to take a walk. And when we take a walk, we add voltages. The fact that that's a voltage source is perfect. The problem is here. If I were to walk down here, I don't know the voltage across the current source. So you're right. That is a supernode. But since I'm not doing nodal, I'm okay. Did I do it all right? Excellent comment. Very good. All right. Now, where's the first equation? I think we're going to start on the bottom left. And what I'm going to do is I'm going to walk around. I can't come down here. Why? Super mesh. I don't know the voltage across this current source. So I walk around the large loop on the bottom. So I'm going to walk over to this side of the board, and I'm going to see if I can write the equation for walking around the bottom portion of the combination of loops 1 and 2. Notice the x. I start at the bottom left. I get minus Vs. Now, my colleagues, there's two ways of writing this. We'll take it one at a time. Plus R1 times I1 minus I3. All right. Now, let me pause. I got minus Vs, and now I come here. And for the moment, I'm ignoring Vx. For the moment. And what I get is that's R1. So I'm walking in the direction of I1. So it's I1 minus I3 times R1. Are we good? Right. I'm walking in the direction of I1. For the moment, let's ignore Vx. And what I have is R1 times I1 minus I3. Parker.
For the moment, we also want to ignore IX. Keep it as I1 and I3.
Right now we can bring them in right now. So as we did with nodal, there's a couple of ways of writing these equations. So Parker, maybe you can help me out. Parker, what I could have written is minus Vs minus Vx. Am I okay with that? Those would be the first two terms. So what I could have done is said minus Vs, and then this is minus Vx. So what do I know Vx is? What I know is Vx equals minus R1 I1 minus I3. Okay, let me just double check before I, Vx is I3 minus I1 times R1, right. My colleagues, I know I have a question. I also see it perhaps a little more easily. This is the positive side of the resistor. So this becomes I3 minus I1 times R1 equals Vx. So an equivalent way is to say this is R1 times I3 minus I1. Okay. Now, I had a question. Parker, did I do okay? Now, Parker, you'll see when I write the equations, not that you have to do it this way, I ignore the Vx's and the Ix's. I just write the equations, and then I go back and solve for these. I find it challenging to do both at the same time, which is what we're doing now. But we now have an equation for Vx. These are equivalent equations. So continuing our journey, I now have plus, going into the second loop, R2 times I2 minus I3. Now, Parker and colleagues, if you don't mind, for the time being, I want to ignore IY. I'm going to come back to it, okay? But I'm now going to say this is plus R3 times I2, then minus B times IX equals 0. Let me check myself. Minus Vs, then I1 minus I3 times R1, plus R2 times I2 minus I3, plus R3 times I2 minus BIX equals 0. That's the first equation. How did we do? Now, yes?
Can you just go over how you know the i's are negative, like how it's negative I3 versus positive I? Like you did it down below fairly well.
I'm sorry?
You see where it says like R1 equals I1 minus I3 up top in our equation? Yes. Now, can you explain how you knew it was positive I1 and negative I3?
Absolutely. And I can continue it here too, okay? So the question is, can I explain these two terms? This is absolutely critical, so make sure I do a good job. All right, I sense you're good starting out minus Vs. Here's the key answer to your question. In this loop, we are walking in the direction of I1. And I1 says, from my, again, forget Vx. From my perspective, I'm walking into the positive end of the resistor. So it's plus R1. Now, I1 minus I3. We're doing it from the perspective of I1. Did I do okay? Now, can you help me? Can you step me through this one? Going the opposite way. Don't even think of the negative end. I3 is going against I2. So it's I2 entering the positive end, for those who didn't hear it on the archive version. I2 minus I3 times R2. How do we do? Thank you. You're more than welcome. All right, now, I have to write the super mesh equation. And Tara, to do that, I go inside, right here. And now I say, I'm told the amount of current flowing down here is AVX. And I say, okay, going down is the key. This becomes I1 minus I2. Okay, so the super mesh equation is AVX equals I1 minus I2. AVX is I1 minus I2. All right. Now, can you write the equation for the upper loop? Okay. Let's see if I can do it. Notice I start where the x is. Again, the x is not on the exam. And I now going to walk around the top loop. I'm thinking of my colleague here who asked the great questions before. I'm starting there, and what I get is I3 times R4. So R4 times I3. Now plus C times IY. And now, here it comes. Now I'm going through R2, but from the perspective of I3. So I get I3 minus I2. Right? And then I go through R1 plus R1 times, from the perspective of I3, it's I3 minus I1, and I'm back to where I started. So at this point, we have 4 equations. We're almost done. All right, let me just double check. Emily, what do you think? Am I doing all right? Just checking it, my colleagues. I'm sorry? The question is, what are the 4 equations? 1, 2, 3, and either one of these. That gets us 4. Okay. Now, can anyone help me? What else do I need here? I got the loop equations. I got Vx. What has to go next? How about Ix? Now, here's the thing. Ix is so simple, it's hard. It's so simple, it's difficult. What's Ix? What's the current in that resistor going in the direction shown? What's Ix? Parker. That's it. Ix is I3 minus I1. We're up to 5 equations. One more and we're done.
Would it be wrong to write it as Ix is equal to Vx over R1?
Right, you could write it that way also. I think the answer key probably had that. So Ix is Vx over R1. Now, it's not wrong, but if we were to ask you to solve these equations, the unknowns are I1, I2, and I3. So you would want to express Ix in terms of, the i's. It's not wrong, though. It's correct. But eventually, if you were solving these, you would have to do another substitution. Did I do okay? Yeah. All right, good. Last equation. What's the one variable? We got Ix. We got Vx. Iy. What's Iy? Tara, can you help me? Emily. I have to learn your colleague's name over here again. What's your name again? Kayla. Kayla. Great. I got the whole front row on this side. This is great. Okay? All right. So Emily, Tara, and Kayla. So Kayla, I'm thinking, Iy is going up. I2 is coming down. Wait a minute. Could it be as simple, Kayla, as saying that Iy is negative I2? I think that's it. Sure. Iy is going up. I2 is coming down. They're opposite. Tara, did I do okay?
Yeah, but I just don't see the difference between that and the Ix, like how you would know it. Like my first instinct would think that it was I3 minus I2.
Right. I3 minus I2. But help me out, Tara. I3 never makes it here.
Okay.
Right? I3 is just contained in this loop. I1, think of it as like a block. I1 is here. I2 is here. And in this part of the block, since there's no neighbor we're sharing with, this is all I2 here. And Iy goes in the other direction. So I3, see, that's why it goes this way. Never makes it down there, Tara. How do we do? All right. I think we've done it. I hope I got the right answers. I'm assuming they're all right. Okay. Iy is minus I2. Ix is I3 minus I1. Vx is R1 times Ix, or R1 times I3 minus I1. AVX is I1 minus I2. R4 I3 CIY plus R2 I3 minus I2 plus R1 I3 minus I2. R1 times I3 minus I1. And the top one is minus VS, R1 I1 minus I3, R2 R3 minus V. Okay, 2 problems done. Now, my colleagues, REQ left was not written on the answer key. REQ right was not written on the answer key. I in was, because that's a controlling variable. All right, determine the value for V out. Now, we had a problem of the week. I think it was very similar to this. Okay? So, I'd like to get V out. I'll give you a moment to copy this down. This is where we need some background music. Danielle, I play the accordion. Maybe I should bring it in next time and have some writing music. We'll just be banging out the keys on the accordion here. All right, now, I'd like to refresh my memory as to how this works. Now, I think we discussed this in class with the problem of the week 1, but let's make sure I did okay. These are really two separate circuits with the exception of this dependent source. And Gina, what I mean by that is all of the current here on the left stays on the left. All of the current on the right stays on the right. And there's a common ground between both of them. Now, my thinking is I need to get the value of V out. So, instinctively, I start on the right side because that's where V out is. And Emily, I see two resistors in parallel, so right away I'm thinking that's an REQ right. And I combine them, product over sum. And I get an equivalent resistor here. So far, so good. Now, I can now do voltage division because I got rid of those two resistors in parallel, and now I have an REQ. Now, my colleagues, both the home audience and the live studio audience, please look over the formula sheet to see what formulas are there and are not. For example, product over the sum is not on the formula sheet. So you have to know that's only valid for two resistors. Now, if I want to do voltage division, I'm going to get V out equals REQ right over 2 kiloohms. Oh, by the way, my colleagues, I did not intend this to be tricky, and a number of people tripped up on it. 2 kiloohms is 2,000. A fair number of people put down 2. So you can't see, on the other side we have like hundreds, here we have thousands. It totally changed their answer. So kiloohms is 1,000. Right? So I then say 2 kiloohms plus REQ right times AIN. Now, I know A, and I know all of this, and you can look at my solutions. You'll get a number. So, Emily, V out is some number times I in. Now, I have to go to the left side. Why? Because that's where I in is. All right? So now I go to the left side and I say, okay, what's I in? So I see 3 resistors in parallel, and I see I in, and I'm saying this is current division. But the formula for current division was messy unless there were two resistors in parallel. So this resistor and this resistor are in parallel. Two resistors in parallel, product over the sum. What's even nice, if they're the same value, it's 1/2. So this becomes 250 in parallel with 120. Now, when I scroll down, you'll see this. But now, what is I in? Now, we got to be careful. What I now see on the left side is 120 in parallel with 250. Do we all see that? Now, Gina, putting you on the spot, you can pass. Don't worry. I see 120 in parallel with 250. I'm going to use current division. Now, voltage division, I put in the numerator the resistor whose value of voltage I wanted. Do you happen to remember, and it's okay if you don't, current division? Gina's giving me the answer telepathically. Gina, you're right. That's right, Gina. Exactly. So, Gina, it's 250. You see, my colleagues, it's 250 over 250 plus 120. Oh! In current division, when I have two resistors in parallel, I don't put the resistor whose current I want, I put the other one. Thank you, Gina. I knew you knew it. And all of this is times not 200 amps, 200 milliamps, which is 10 to the minus 3. So, if you scroll down, now Emily, we now get I in to be a number. I take this number and put it in here and solve, and I get V out is given. Part A of problem 3 is done. Danielle, how can I be of assistance?
Just checking that Miller was 10 to the third.
You got it. Miller is 10 to the minus 3. Kilo, K-I-L-O, is 10 to the third. You might have said kilo, forgive me. Milli is 10 to the minus 3. Perfect. All right. So now you're cruising along, and then your eyes light up in delight and joy. A load resistor is placed between terminals A and B. Oh, this sounds familiar. We want to select the value of the load resistance. Ding, 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 ding. Whoop, whoop, whoop. Alert, alert, warning, warning. Maximum power being delivered to the load resistance. What kind of problem is this? Devidan. Devidan. Or as Emily says, Thavian. Okay? I love it. We now call it Thavian from here on out. No more Thevenin. All right? You have a good sense of humor, Emily. All right, good. So now, I have to determine the open circuit. But I say, wait. I did. That's V open circuit. I just got V out in part A. Yes! V open circuit done. What else do I need to determine? I short circuit Tara. Excellent. So Tara, I need to now put a short circuit here. Now I need help before we even look at the answer. The current comes out of this voltage source, goes to this resistor. It gets here. Where does it go? What's I short circuit? AI in divided by 2,000. I know I in from part 1. I'm given A. I say, this isn't bad. It was meant to intimidate, but it's not. Look at this. I short circuit is AI in over 2,000, not 2. I in from part A is a little over 135 milliamps. Plug everything in, 0.0101 amps. Parker, can I put you on the spot? And this is very unfair because we just covered it today in lecture. How do I now get R Thevenin?
R Thevenin, I know this.
That's right.
Just did this on.
That's it. He knows. Again, he's going to tell me
Okay, so R Thevenin is equal to.
the suspense is building. He's a theatrical master. He knows the audience is now bending over, raising the volume on the audio.
Equal to VOC divided by ISC.
Yes, V open circuit divided by I short circuit. And we now know it. So the maximum power for load resistance is 1414.4. So Kayla, out of all the resistors in the world, out of all the gin joints in all the world, she had to come into mind. Do you know what movie that's from? It's paraphrased. No, you have no. Cultural gap. All right, we'll have to watch Casablanca. We'll have to have a movie night. Have you ever seen Casablanca? You have no idea what I'm talking about. You do? Who's seen it? Jerry? Okay. Okay, we'll have to have like a a faculty student. Danielle, can we set this up? Get a showing of like, you know, three of my favorite movies, one every month. Would that be? Kevin Ryan movie night. All right. My colleagues, maximum power, that says to get maximum power from the circuit, there's only one resistor guaranteed to give me that maximum power. That is 1414.4. Now, you may think that we're done with the problem, but no. What's the last part of this problem? You determined VOC. You determined I short circuit. You determined R Thevenin. What's the last thing I'm going to ask you? That's right. It's the power delivered to the load resistor. Okay? Now, my colleagues, I went over this in class today on Monday, February 12th. Let me do it again because I always have to see something more than once. What did the Thevenin theorem tell me? That complicated circuit. What complicated circuit? This complicated circuit. My good man can be replaced by this. Now, I add a load resistor for maximum power. Oh, I don't know if I specifically mentioned it. Forgive me. We calculated R Thevenin. What's the load resistance for maximum power? R load equals R Thevenin. So this R load equals R Thevenin for maximum power. That's what it has to be. Now, I'm asked to get the power to this resistor. Kayla, this is the voltage across that resistor. So I say, okay, wait a minute. I know the power is V squared over R. Now, I need someone to help me because this is easy, and sometimes it's so easy we miss it. If this is V Thevenin, and this is R Thevenin, and this is R Thevenin, what's this voltage across the load resistor? Yes, why?
Because those two resistances are equal, the two resistors are equal, so if equal, the voltage has to equally go over both resistors.
Perfect. Since the resistors are equal, it has to equally divide. So instead of V squared over R, I get V Thevenin over 2 squared divided by R Thevenin. Dun, dun, dun. That's the answer to part C. How are we doing? All right. Now, before the exam, I had a sneaky suspicion that some colleagues didn't understand what I just wrote. And all they remembered was, when he asked me for power, I'm going to write down v squared Thevenin over 4RT. Why? I have no idea, but it's right. Okay? So I sensed this in the force. And I said, how could I prove myself right or wrong? So I came up with another verse to the song, another part of the problem. And here's what I said. You're going to think I'm very devious. Suppose one of your colleagues who has not taken the course incorrectly determines that the answer should be 2 times R Thevenin. So your colleague who has missed this class, they say, oh, no, you're wrong. Our load should be 2R Thevenin. That's wrong. That's wrong. Okay? But let's go with it. And what would they calculate for the power? So now I'm saying someone's made a mistake. And what's going to be the power they calculate if they select our load to be 2R Thevenin? Now, Parker, what's the voltage V? That's exactly right. 2R Thevenin over 2R Thevenin plus R Thevenin times V Thevenin, voltage division. So 2RT over 3RT, it's 2/3 VT. Now, Danielle, what's the power? The power is V squared over R. So that's now 2/3 times VT squared over R. Different answer. So they couldn't have used the shortcut that they thought might have been right. And that's it. Now we get this. So I threw a curveball. I'm allowed to throw a curveball. You know, breaking pitch inside, it's okay. As long as I don't hit you. All right? So I threw an inside curve. Hope that's okay. I don't want to get the lacrosse team mad at me. I could be in big trouble. Gina, how we doing?
Good, but that's a screwball. That's not a curveball.
Oh, look at this. Gina with the, I love it. Gina, I have much to learn from you, Master Jedi of the pitches. I have much to learn. We will have to, so next time I won't make this mistake. I like it, Gina. Not only is she famous for the G matrix, she is now famous for many things of beyond the course. You don't see, the other section doesn't know what the G matrix is. So we'll have to, okay? Thank you, Gina. Are we good? Now, tell you what, we got one last problem. Okay. Was that Tara? Yeah. Tara. That's okay. That's what friends are for, Tara. Tara, here's the deal. Tara, if I were to say what resistor do we put here for maximum power? R Thevenin. Agreed? Now, what is the voltage across this if this is R Thevenin? It splits equally. I know you know this part, but this is just getting me warmed up to the next part. V is V Thevenin over 2. And then what's the power? The power is V squared over R. And we plug this in, and it becomes V Thevenin over 2 squared divided by R load, or R Thevenin, they're equal. Everyone had this memorized. I didn't know if they understood it. So I now come to the last part of the problem. And I say, Tara, as hard as this might be to believe, suppose someone has attended none of my lectures and they get the mistaken impression that our load should be 2 times RT. Now, that's not right. That's wrong. But this person is out in left field trying to catch a screwball hit by a right-handed batter. She's busy. Okay? All right. Tara, am I doing okay? So now they put the wrong value. So now you say, okay, go ahead and calculate the power. Now, just so you know, Tara, doing it the right way, we got 36.1 milliwatts, okay? So we say to this colleague of ours, go ahead, calculate. You're not going to get bigger than 36.1 milliwatts. So what they do, the trick is, what's the voltage across this resistor? Use voltage division. The voltage is 2RT over RT plus 2RT times VT. We have numbers for everything, and we plug it in. See? So it's 2/3 V Thevenin, 2/3 V out. Now, what's the power? V squared over R. What's R? 2RT. Did I have the 2 written down before? No, my bad. I'm glad you asked this, Tara. My bad. It's V squared over R. My bad. The R is 2RT. Tara, my fault. It wasn't your understanding. It was my mistake. I'm glad you caught it because people were yelling at me on screen. I couldn't hear it. So it's V squared over R, but R is 2RT. And notice if I plug in the numbers, I get a smaller answer than I did when I did it with the right value of resistance. Tara, I thank you. Did I answer your question? I think you helped me more than I helped you. We're good? Fantastic. All right, last question, okay? Now, let me not show you the solution yet. This is the quiz one without the work done. All right. Consider the circuit below. Determine an expression for Vs over In. Okay. Now, I say, first of all, hint. You can do this. Okay. I have confidence. Secondly, first, use KCL at node 1. And I say, put yourself in the node. Then take a walk around the loop on the left. Should we let her in? What's the password? We're having a vote. They're unanimous. We should let you in. Welcome back. Welcome back. All right. All right. My colleagues, let's follow the hints. So, Jonathan, I'm just going to get an eraser. I'm coming back to this side of the board, Jonathan. So I'm going to come back to the other side. I'm going to catch you. Jonathan is... All right. So, what are you asking for? What am I asking for? Vs over In. So you're looking at this, you maybe got 12 minutes left in the exam, and you're panicking, but I give you a pep talk. You can do this. Then I say, first, use KCL at node 1. So where do I put myself for peace? In the node. Exactly right, Emily. So I'm now in the node. Kayla, I got this. What I get is, what is the current that goes in? I in. Okay. Plus A I in. A times I in. Excuse me. Okay. The current that comes out of this node right here is I in plus AI in. Do we agree? Okay. So this is the current out of node 1. Okay? So I've done that. Then take a walk. So I'm going to take a walk. Me being me, I start bottom left. What do I get? Minus Vs plus R1 times I in plus, what's the current through R2? Exactly, Parker. R2 times I in plus AI in plus R3 times I in plus AI in equals 0. No, forgive me. Maybe I should have done, let's call this current I1. The current that comes out of the node is I1. So this current out of node, let's just call this for notation I1. And then notice, and this is the key point, what's the current through R2? I1. What's the current through R3? I1. Well, what's the current through up here? I in. Did we do okay? So now, what I get is R1 times I in plus, let me factor out the I in here. This is R2 times I in outside of 1 plus A plus R3 times I in outside of 1 plus A equals Vs. Now what am I looking for? Vs over I in. I got it. Factor out the I in, Danielle. I in. So what we get is the answer is R1 plus R2 times 1 plus A plus R3 times 1 plus A. And that's what's written in the solutions. The question is, do we take our test next class?
No, in class.
Yes, in class, sorry. All right. So, did I get the quote-unquote right answer? Vs over I in is R1 plus R2 times 1 plus A plus R3 times 1 plus A. It's the same thing, right? 1 plus A times R2, then plus 1 plus A times R3, Vs over I in. That was the exam. What do you think? Easy, medium, hard?
With you here, it's easy.
Well, I'll be with you in the exam, too. Any last questions before I pack up and Jonathan says adieu? Yes?
Will the exam have the same kind of concepts tested for each individual problem? Like 1, 2, 3, 4 will be nodal?
No, I can't commit to that. In fact, I'm very careful what I commit to because I've been held to it, and sometimes it's not what I meant. What's on the exam is chapters 1 and 2. Now, if you leave here tonight thinking this is the only way I can ask those questions, no. You need to look at least 3 to 5 exams. Okay, there's other ways to ask nodal and mesh and amplifier and Thevenin, and there may be another topic, like, for example, I could give a question just on voltage or current division. So this was a sample, the most recent sample, but I have freedom to pick anything from chapters 1 and 2 and put them in any order. Help.
Is there an equation sheet attached to this file?
Yes, if you look at this, I must have put it on the exam. Oh, wait a minute. This is exam 1. I beg your pardon. Exam 1, we don't have a formula sheet. We don't need it. That takes care of that. We don't need a formula sheet. No security blanket. This is engineering. There's no security blanket. We're still recording, I hope. Good. So there's no formula sheet. I was wrong. Jerry. That's true. Heated security blankets. All right. My colleagues, anything else? All right. They're coming to take me away. All right. I want to say thank you to Jonathan and all his colleagues at SIT TV. Let's hear it. Whoa. Thanks, everybody. Was it worth your while? Yeah. Now, listen. If you watch the video, think about giving me a like. It's not required. But like I think I told you, I had 300. Huh? I don't know. Last year, I think I had like 9 likes out of 400 views. I was crushed. I went home and had ice cream. I don't know what I was doing. I was depressed.
Maybe those 9 people watched it 400 times.
No, I don't think so. You're being very generous in your